Okay. Hello everyone. Welcome to our COFFIES seminar again for October, which is the month of us kind of for the heliophysics big year. This month's theme is the solar cycle and solar max, which we will have a seminar on the same topic today from our barista Lisa. So everyone should know Lisa, I assume. But just in case to our friends outside of COFFIES or who just view the seminar online, I will still have an introduction of Lisa. So Dr. Lisa Upton is currently a lead scientist at Southwest Research Institute in Boulder, Colorado. She received her PhD in physics from Vanderbilt University in 2014, where she worked on the magnetic flux transport in the sun's photosphere. Lisa is one of the original authors of the advective flux transport model, which she now uses to investigate surface flux transport processes and make solar cycle predictions. She serves as the co-chair to the NASA NOAA Solar Cycle 25 prediction panel. Her research interests include understanding the solar dynamo, solar cycle variability, and the impact on the Sun-Earth environment. Let's thank Lisa again, and Lisa, I will pass it on to you.
Thank you so much, Riju. Thank you everyone for coming today. It's a topic that's near and dear to my heart, so I was very excited to be able to talk to you today about this month's NASA Heliophysics Big Year theme. Also, I just want to mention in honor of this topic kind of being, I think, a big topic for all of us really as members of COFFIES. I think COFFIES is also going to be participating in this month's Heliophysics Big Year. We've also added a new website, a new web page to the COFFIES website. So if you haven't seen that yet, go take a look. We've got some activities we'll be planning for this month, and so stay tuned for more information on that. All right, so let's go ahead and get started. I also want to just quickly mention that a lot of this work is work that I've done in collaboration with David Hathaway, so I want to make sure to give him credit and thank him for his contributions to this as well. All right, so let's cut to the chase. What is the solar cycle doing? So here is a picture from the NASA NOAA, or the NOAA Solar Cycle 25 progress page, and we can see how the solar cycle is faring compared to our predictions. I just remind you to kind of disregard that red line. We're actually more looking at the left edge of this curve as being aligned with kind of where we are with that prediction. So because we had a predictive range of 115 plus or minus 10, with minimum occurring at April of 2020 plus or minus 6 months. And since we know that the minimum actually was at the very beginning of that predictive range, when we compare the solar cycle to that solar cycle progress, we want to make sure that we're looking at that leading edge, which is more representative of that solar cycle beginning at the beginning of that predictive range. So we do see that the solar cycle is a little bit larger than what we predicted, but not significantly so. Just put it in a little more context. I'm just going to show you the last several solar cycles. And what we see is that solar cycle 25 is shaping up to be a little bit larger than 24, but we really don't expect it to reach the average size of what we saw for cycle 23, which is a kind of a prototypical average cycle, or one of the larger cycles that you see in 21 or 22. So it is still very much consistent with a very small, with a small cycle, even though it is slightly larger than what we predicted. So just to get into a little bit of the science, I think most of you are all aware of this, but just in case there's any early careers online, just give you a brief rundown of how we believe the solar cycle works. This is a phenomenological model that was coined by Babcock back in 1961 to help explain all of the activity that we see on the sun. And the idea is that we start with a sun with a very dipolar configuration. You have a north-south field that looks very much like a bar magnet. And this corresponds to where we are in solar cycle minimum with a very weak dipolar field. The flows on the sun interact with the magnetic field that's threading through the interior, through the convection zone. The differential rotation acts to shear the submerged magnetic field in the toroidal direction, which stretches it out into an east-west orientation. This stretching process causes that magnetic field to become stronger, to become buoyant, and emerge in the form of sunspots or active regions with the characteristic Joy's law tilt and Hale's polarity. The magnetic flux from these active regions is shredded off by the turbulent convective motions and is redistributed on the sun via all of the flows, the convective flows, differential rotation, and the meridional flow. The last of those, the meridional flow, acts to transport following polarity, typically, to the poles. This leaves a little bit of excess polarity at the equator that will end up canceling, and this will subsequently build up a new polar field with the opposite configuration, and then we repeat the cycle over and over again. So this process where we convert this north-south oriented dipolar field, stretch it out and emerge it into forming the active regions is somewhat of a linear process. It's not completely linear because it's interacting with the convective motions, but it's somewhat linear. And so we know that the strength of these polar fields at the time of minimum are strongly correlated to the strength of the cycle. And that kind of makes sense because that seed field is really the basis for creating that solar cycle. And so the predominant feature this is the predominant feature that we look at when we are interested in making solar cycle predictions. It's these polar fields. And we can do this in a number of different ways. The longest method of doing this is by looking at the geomagnetic AA index, and that's what I've plotted here at the top at this figure here. The geomagnetic AA index, in particular at the time of solar minimum, is strongly correlated with the strength of that axial dipole, that polar field that's occurring at the sun, because there's little variability that's occurring between the time it gets where it's leaving the sun to when it gets to the Earth. So there's a very strong correlation between the polar fields and that AA index. And so this has been a very long-lived metric for looking at the amplitude of the next cycle. However, this geomagnetic AA index is not quite directly the polar fields that we really want to look at, which are the source of the strength of the next cycle. To look at it more directly, we really want to look at the polar fields at the sun. And we can do this with two different ways. We can look at the axial dipole moment. And so this is a single calculation that is a measure of the strength and orientation of that dipolar magnetic field. And that's this middle plot that you see here. And we see again that this is very strongly correlated with the strength of the next cycle. Or we could measure the strength of the polar fields by measuring all of the magnetic flux above a specific latitude, typically taken to be 55 or 60 degrees, and plot that as a function of time for both hemispheres. And again, we see that there's a strong correlation between that north-south asymmetry and the difference between the north-south and the strength of that next cycle. So again, another way that we can look at the polar fields and get a sense for what we expect for the next cycle. If we do this, we can plot these values as a function of the strength of the next cycle and develop a correlation that will give us an idea of what we might expect for the next solar cycle. We take the geomagnetic AA index at its minimum value, and we get a prediction for solar cycle 25 that the cycle will be about 132 plus or minus 8. And if we look at the polar fields, we get, if we look at the axial dipole, we get a 114 plus or minus 15. And if we look at the polar field strengths, we get 120 plus or minus 10. If we scrunch all of these together into a single value, we get a variance weighted mean of a cycle that's 125 plus or minus 6. Again, this is a little bit larger than what the panel had predicted, but not significantly so. It's certainly well and consistent with the all of those predictions.
Can I interrupt, Lisa?
Yes, please, Yiming.
Yeah. I notice in your plots here, you forced the line to go through 0,
Yes.
the origin.
Yes.
Now, I don't think that's necessary. I mean, I don't even think that's a good idea.
Yeah, that's fair.
Because it may be that when the sunspot number is 0, there's still, there's still polar field.
Right, right.
So,
absolutely. That could be.
So I made predictions, as you probably know, where using the AA index and polar field and radio interplanetary field strength.
Yeah.
I just did a least squares fit to the points. I found significantly higher values of Rmax, like of about 10 higher.
So you're saying something more like what we have here for the
140.
geomagnetic A index, the 132 plus or minus 8?
The AA index, I found values between, 146 and 153.
Great.
And the interplanetary field between 136 and 46. But they're significantly higher than yours.
Okay. You said 146?
AA index, I used 2 different versions, one for Lockwood. So I got 146 to 153.
Okay, yeah, 153 is quite a bit larger, but I think still smaller than the average cycle of 20 of what we saw.
Oh yeah, no, I'm not disputing that,
yeah.
but
I'll get into a little bit more about what are all the why do we have all of these discrepancies? So if you'll let me continue, let's chat about it some more. Okay, so we've got these different methods that we could use, and some of the ones that Yiming mentioned. After the cycle, and these are all methods that we can do once we get to minimum. We can look at all of these values. Now, once we've actually gotten into the solar cycle, a couple of years into the solar cycle, we can start to use a curve fitting technique. And this was proposed by David Hathaway back in 1994. And he found that you can make a parametric fit to the solar cycle using 4 parameters: the amplitude, the rise time, the asymmetry, and the start time. Digging a little bit deeper, he found that the asymmetry parameter A could be fixed for all of the cycles, and that the rise time parameter could be expressed in terms of the amplitude. And this is the well-known effect that we see that big cycles rise very quickly, whereas weaker cycles are shorter to build up. And so this allows the solar cycle to be fit with just 2 parameters. And so we've updated this fitting function for sunspot number version 2.0. So since we're all using 2.0 instead of the older sunspot number version. We've taken a look at how accurate is this curve fitting technique as a function of how far you are into the solar cycle. And so that's what we have plotted here. It's basically the ratio of the predicted amplitude over the final amplitude. And you see when you're about 2 years in, you still have quite a bit of scatter across this, a lot of variability. But by the time you get about 3 years in, you're down to about within 10% of the final fit values. And then as you progress even further into the cycle, you get convergence until you get pretty much right dead on. So the curve fitting method, if we looked at just that, we find that the fitting results for cycle 25 were very variable and quite uncertain up until about May of 2022. So that corresponded to about 30 months after minimum. Since then, the results have basically not changed at all. And the curve fitting method has given us about a 135 plus or minus 10. We can merge this in with all of our other prediction methods, and we can find that the combined sunspot number prediction based on all of the precursors, based on the curve fitting at 30 months into the cycle, gives us a value of about 134 plus or minus 8. And this was a result we published last year, in addition to a description of all of these different methods that I've outlined before. And again, we see that this is slightly bigger than what the panel had predicted. And it also seemed to indicate that we would be having solar maximum about now, fall of 2024. So I want to dig into this a little bit deeper before I compare with what we're actually looking at today, by looking at this difference that we see, and some of those differences that Yiming brought up earlier is why is the AA index so much higher than what we got from the WSO axial dipole measurement? Why is there a difference between these different precursor methods? I mean, that's pretty significant, 114 to 132, and then Yiming's 150. There's some it's not a trivial amount. And so looking into it a little bit further, we want to look at, what is the motivation behind the work that we're doing? And really, when we're convening a panel, Solar Cycle 25 prediction panel, we're doing this well before minimum. And so we have to rely on methods that allow us to make predictions, well before we're actually getting to solar cycle minimum. And really, to do that, you can't really look at the geomagnetic AA index because you're not really, we're not going to be able to get to that value. But if we look more directly at the polar field measurements, we can use simulations, we can use dynamo models, we can use surface flux transport models to extend these predictions earlier in time by predicting what the evolutions of those polar fields will look like in the coming years. And so we can do a pretty good job, 3 to 5 years. I say we can get an idea of what those polar fields might look like. And then about 2 years in, I think we really start to hone in on them. And so we've kind of moved away, at least for this last prediction panel, from really focusing on that geomagnetic index and more focusing on the last few years of the solar cycle, or the last few solar cycles. And so unfortunately, that means we lose this longevity that's associated with this AA index. It gives us a much better correlation than fitting with just three or 4 points of the last few solar cycles. But it actually is worse than that. So we really have only had polar, good, consistent polar field measurements really since WSO, the Wilcox Solar Observatory, really started taking measurements in the about 4 or 5 decades now, maybe 5 decades now ago. And so WSO has really served as our yardstick for this parameter that we're using to make these predictions for the polar fields. And because it's the only one that has any kind of consistency and longevity associated with these measurements. Unfortunately, because this was half a century ago, technology was not as good as it is today, and so this instrument is really using 1 pixel to measure nominally 55 degrees and above, to make that measurement of the polar fields over time. And so the problem in that lies in the fact that as the Earth orbits the sun and the latitudes measured by that most poleward pixel, 55 degrees and above, are actually changing in time. So over the course of the year, it's sampling lower or higher latitudes and more or less of that newer polarity flux, or the older polarity flux that would be present in that pixel as it's oscillating over the orbit. So consequently, the average polar field strength measured by that pixel changes significantly over the course of this orbit. And that results in an annual oscillation in that measurement. And so really to give you a context, instead of measuring 55 degrees and above, we're really, that lower limit is oscillating between 48 degrees and above and 62 degrees and above. And so as I said, that gives you these really big oscillations in this measurement. And these deviations in the polar field measurements tend to be most notable when the polar fields are rapidly evolving, i.e. when the polar fields are reversing. And that makes sense because when the polar fields are reversing, you're pushing more flux up to those higher latitudes. And so you're going to have a much bigger gradient over that pixel as it's moving up and down over those latitude bends. And so that's what produces this annual oscillation that you see that swings very large as those polar fields are actively reversing. Now then, one might expect that, we're taking the measurements over the course of the year, so we should just average it out and they will all cancel out. And then the northern and southern hemispheres will, they're kind of out of phase with each other. And so, we always have one of the poles that's favorable, but unfortunately, it doesn't work out that way because there's a systematic effect in that the unfavorable pole always appears ahead of the polar reversal because of those lower latitudes that are being included and having more of that new polarity flux. And so this means that if we're, for instance, are looking at the axial dipole moment from measured from WSO, that at nearly all times, one of the two poles is going to appear to be ahead of the game. And so thus the evolution of the axial dipole is going to essentially precede the true polar field evolution in time. And we see this when we compare the WSO measurements with, for instance, MDI or HMI. As those polar fields are actively reversing, it's always ahead of the game. It's predicting it before ahead of what the HMI or MDI are giving us because they have much better resolution. And so this systematic effect is coming into our measurements. We can see here that if we scale, so in this case, I've scaled the HMI and MDI measurements to be consistent at the time of minimum. So at 2010, we're matching up. At 2020, we're matching up. What we see is that for this most recent time of minimum, there was about a 20% difference between what WSO was seeing and what we're seeing with HMI and MDI. Now, I think most of us who were making predictions, that were using models to guess what that polar field would be, are kind of scaling them to the HMI. And so if you're using HMI as your data assimilation, that's going to help you get the closest connection to what we're going to see, you end up getting a polar field that's about 20% weaker than what was actually observed in by WSO, which is what we're using as our yardstick to make this relationship. And so this uncertainty in the polar field measurements translates into uncertainty in the polar field to cycle strength relationship. Again, as Yiming pointed out, with only 3 data points, you could fit it to 0, you could fit it to some number, but without more data points, it's really hard to really rely on this relationship. There's just so much uncertainty inherent in this relationship. Whereas with the geomagnetic index, we've got 13, over a dozen cycles, and so we can get a pretty strong correlation between those values. So this uncertainty in our yardstick needs to be taken into consideration when we do our future cycle predictions. We need
Can I interrupt again, Lisa?
Yes.
About the AA index.
Yeah.
The AA index at near solar minimum is almost entirely a function of the axial dipole moment.
Correct.
And the axial dipole moment is actually the interplanetary field strength, the radial interplanetary field strength, is a very excellent measure of the axial
Absolutely.
moment.
Absolutely. I think that's what I said earlier in the talk.
So therefore, I think the best predictor is not the polar fields, but the interplanetary field strength at minimum.
But again, The problem with that is that you really need the minimum value in the geomagnetic AA index, which typically doesn't occur
Yeah,
until after you
okay.
get to after you've passed solar cycle
I
minimum.
agree.
So if
You don't know the minimum value until
yeah.
the minimum.
And so you
So
really can't use that very well until after you've gotten past solar cycle minimum. And so for people who are wanting to make predictions, we're relying on these other metrics. And you're absolutely right. If you're looking at the spread of these data, you're looking at this relationship. We've got over a dozen solar cycles that have been well calibrated to get this relationship compared to 3 cycles. I mean, how much can you really rely on a relationship with only 3 to 4 data points? And so, this is, when we are making predictions, if we're going to rely on this measurement to get at what the polar fields might be, 3, 4, 5 years ahead of cycle minimum, we need to make sure that we're taking into consideration this uncertainty that's inherent in these measurements. When we need to get to the poles, we need to have better polar field measurements, and we need these measurements for a long time, many, many cycles before we're going to be able to have the kind of accuracy in this relationship that we have for the geomagnetic AA index. We're way behind the game in terms of these polar fields. So we need these consistent, sustained ground observations for a really long time. And this is really a fundamental necessity if we're going to rely on this relationship to be our predictor of the next cycle. We've got to do a better job of calibrating our yardstick and reducing that uncertainty. Until we do, you're absolutely right, that geomagnetic AA index is going to do a better job of giving us a good picture of what the next cycle or what the cycle ahead of us goes. So, with all that being said, David and I had this paper that came out last year. I gave several talks in that time, and this is the prediction that we were sharing with everyone. At that time, I was mentioning that we were having we just had this huge spike that was in June of 2023. It was getting a lot of press, a lot in the media. The sun is spiking. We're jumping to a much bigger cycle. But I think these spikes are a normal aspect of the solar cycle. This is part of this quasi-biennial oscillation that Karen Jane, that Mausumi Dekpati have been looking into. And these spikes, this 1 to 2 year periodicity that's superimposed on the 11-year periodicity is normal. And so we really can't rely on the peak of this one spike to really make this measurement. This is why we do a 13-month smoothing when we are talking about the solar cycles, to smooth out this variability. And so a year ago, I was saying to expect another another spike like this in about a year or two, and then that I thought, after that spike, we'd probably start to see a decline. So let's take a look at what the cycle is looking at now. How did this prediction from a year ago fare to what we're doing? And as you may have, if you've been paying attention to the sun, you know that we've had a recent outburst of activity. This past May, we had a tremendous geomagnetic storm that impacted us all. We got many of us got to see beautiful aurora. Some of us for the first time ever in our lives, and that spike in activity has continued. We've seen more sunspots over the last 6 months than we've seen previously in this cycle. And in fact, in August this past year, we had a peak of about 200, I think it was 214 in this sunspot number. And so this is that second spike that I had mentioned. And so one of the things that we want to look at, I think in the past I was saying, okay, well, we would have this spike, and then we'd have this another spike, and then we will really start to see that decline. But I think another thing that we need to look a little bit closer at this quasi-biennial oscillation. I'm so glad many of our COFFIES members are doing this, because I think we really don't have a good fundamental understanding of what is the source of this quasi-biennial oscillations, these QBOs, and we really haven't looked very deeply into how does that QBO interact with the larger 11-year solar cycle. And so, in the past, I'd said that I thought, well, maybe, we'll be kind of like cycle 24. You'll have this spike, and then we'll have another spike, and then we'll probably see a decline. But looking at it more closely, I'm thinking that maybe not. Maybe we'll actually have a third spike that appears. And I think what happens is when you have these spikes occurring on the shoulders of the larger 11-year periodicity, they're somewhat dampened. Whereas when you have a spike that's occurring right at the time of maximum, it's kind of amplified. And so it's possible, and even I think likely, that we might see another third spike coming about a year from now. I expect that third spike will probably be smaller than the one that we've just experienced, and then we'll be heading into the declining phase throughout that time period. And so just to kind of give you some context, I'm just doing some showing you a comparison with some other cycles that had this kind of behavior. We had a spike early on, this really large spike that occurred right at the time of solar maximum, and then one or two other spikes as we're going into the declining phase. Again, a spike in the rising phase, a fairly large spike occurring almost coinciding directly at the time of maximum, another spike as you're going into the declining phase, and then that QBO becomes less apparent as the cycle progresses, but I think it's still somewhat there. So I think this is a really interesting aspect to the solar cycle and how that interacts with this 11-year periodicity. I think we need to do a little bit more work on understanding that. I also want to take a look at the polar fields and how do they look now. So right now, this is the HMI polar fields, and we see that both hemispheres have actually reversed. Both the North Pole and the South Pole have reversed polarities and are starting to increase. We see a fairly good increase in the polar fields in the South, and the North are working their way up. This reversal of the polar fields tends to occur about a year or within a year of the solar cycle maximum. And so this is another indication that we should expect that we are currently in maximum and are heading into the declining phase. So we're at solar cycle maximum. I even posit to say that peak that we experience is going to be the largest sunspot number that we'll have. We do have to be careful though, because when we do declare the peak in the solar cycle, we have to do that 13-month smoothing, which means you got to wait about another 6 months to a year before we can say for sure where exactly the peak of the cycle is. And depending on how things progress over the next several months, it could be a little bit before, a little bit after that spike, depending on how that curve, that smoothing works out. But we are at solar cycle maximum now. Expect things to decline, possibly another spike as we're heading into this declining phase. And so the next thing I want to look at, and so this is our most recent prediction that David and I put up on our website just this month, and so you can see we're looking like we're right at maximum now. So the next question, obviously, is what can we expect for solar cycle 26? Well, unfortunately, we're still a little bit too early to really make any meaningful predictions about what we might expect for solar cycle 26. We're only about halfway through the cycle, so we've probably got about another 5 years to go before we get to the next solar cycle minimum, maybe a little bit more. And you really don't start to get an indication of what that might be until you get about 3, heading into 5. Maybe we can start doing, get an indication of what we might expect, but it really, you can't get any kind of accuracy until you get about 2 years prior. That being said, in addition to these QBOs, we know that there's other signals superimposed on the solar cycle. And so we have this 100-year, this 80 to 100-year periodicity that we've seen in the historical record, where you've got this ebb and flow on that kind of time scale. And so we probably are just coming out of the most recent Gleisberg minimum. And so we might expect that the next several cycles will be a little bit larger. We might see increasing cycles in the cycles to come, which will be great. So just quickly go over my conclusions. Solar cycle 25 is still on track to be a fairly weak cycle, only slightly bigger than cycle 24. We're at maximum now, yay! We do need better polar field measurements. We really need to get to the poles to find out what they are. We need to calibrate this relationship, our yardstick, so that we can reduce the uncertainty associated with that. To do that, we've got to have consistency and longevity in our observations. So thank you to all the people that are working at WSO and making those observations. They're vital to us. The polar fields have reversed, so the cycle is well on its way, and we should start to see the cycle decline, possibly another spike in activity in about a year or so. And so with that, I see that there are already a lot of questions in the chat. I've tried to save plenty of room for discussions because I'm curious to hear what all of you have to say. And so I guess, should we take some questions?
Well, I have another comment.
Sure.
About calibrating the polar field strength at solar minimum.
Yeah.
As I said earlier, the radial interplanetary field strength near solar minimum depends almost entirely on the actual dipole moment.
Yeah.
And therefore, you can use the IMF strength to, as a constraint on your polar field measurements.
Absolutely. Yeah. Do you know, has anybody done that?
Well,
done that?
I mean, I've looked at the relationship between the IMF strength, the radial IMF strength, the Mount Wilson polar field measurements, and the Wilcox polar field measurements at solar minimum.
Yeah.
That covers 4 or 5 cycles. So minimum.
Yeah.
And I found that there's some discrepancy, especially between the WSO measurements in some of the earlier cycles and the IMF measurements.
I'm not surprised. Again, heading back to this effect that I mentioned earlier, as far as the measurements not being quite timed right, and I think that's one thing that we need to do is calibrate those measurements better to our more modern instruments. If we can get WSO calibrated to HMI and MDI and somehow pull out that variability associated with that annual oscillation, pull out that oscillation, perhaps we'll get a better relationship there.
Sushant has his hand raised and has asked a couple questions in the chat. So Sushant, do you want to go next?
Yeah, I was just going to reiterate the ones in the chat. A couple questions. Well, first, very nice talk, Lisa. Beautiful figures as always. Is there a known delay between the polar field reversal and the maximum of the sunspot number? Does one happen before the other?
I think typically, let's see, I believe typically the reversal, it comes a little bit maybe after the maximum, but I don't know for certain. I'd have to look in that a little bit further. I haven't seen any literature that has looked at has quantified that relationship, but that doesn't mean it's not out there. I know that they don't always coincide exactly, that they usually are pretty close. I seem to recall hearing that maybe the reversal comes a little bit after the maximum, but I'm not positive of that.
It also gets complicated by like the hemispheric asymmetry and that sort of thing. So
yeah, that definitely complicates things. I mean, when your cycles are a significant asymmetry, we saw that for solar cycle 24, there was a significant hemispheric asymmetry. That's not so much with cycle 25 so far, though. So,
but it's also complicated by the fact that a lot of the maxima are double peaked. So
Right.
for instance, cycle 24 was
Mhm.
double peaked, and the biggest peak was 2014, and that was
Yeah.
after polar field reversal.
Right. But
And
but
it-
that one actually was very strongly related to the hemispheric asymmetry. There was a huge, like two to three here asymmetry in the reversal of those polar fields. It was very prominent. Not so much in the other cycles. The hemispheric asymmetry was much smaller. But those double peaks that we see, those appear in the hemispheric data. If you separate the sunspot number between the south and the north and the south, you get those double peaks. And again, I think this points back to these QBOs and really getting a better understanding of where do they come from, and how do they interact with the longer cycle.
Mhm. Thanks. And the other question I had was, what are the competing theories that try to explain the 100-year period?
Oh,
Are there any?
I don't think I could really do that justice. I mean, certainly, there are skeptics that say that, just that with the fundamental periodicity of the cycle and the stochastic, variability inherent in that, you're just by natural random, you're from time to time, you're going to get this kind of apparent scale to those oscillations. I don't know that there's anything that's really concrete as far as an understanding of what that might be. I think another idea behind that might be that there's saturation mechanisms in place that once you get to a low enough cycle, there's some kind of saturation that will occur that will kind of kick you back up again and start you heading to increasing cycles. And then once you get to some kind of higher, maximum kind of cycle level, there's some kind of saturation that will send you back down. And if those are operating pretty consistently, then you might expect some kind of regular periodicity to show up. But as far as I'm aware, there's not anything definitive or concrete in terms of understanding that. I don't know, does anybody in the audience have any other any evidence to the contrary, any knowledge to the contrary?
Yeah, so I think it's noise. At least it's consistent with noise.
Yeah,
You put in the simplest model of noise you can come up with, and it produces superior, it
Right.
produces the features you see.
Yeah.
And we have several papers on this with Manford.
Yeah, certainly. I mean, like I said, I mean, there are skeptics that believe that. I tend to lean more towards thinking that there might be some saturation mechanisms that might be producing that kind of periodicity. But yeah, I don't think it's been determined with any kind of certainty.
We more or less know the noise which goes into a cycle,
Yeah,
and this is enough to reproduce what we see.
sure.
So if people want to argue there's an additional periodicity,
Yeah,
they have to show that it's significantly above what we see, which is
right.
Have you done simulations to show this?
Oh yeah, yes. We've done simulations, and we've done an analysis showing how you get all the features of the power spectra with a noisy normal form Hopf bifurcation. This
Yeah,
is Cameron and Schuster, maybe 2018, something like this. But we did the Babcock-Leighton dynamo model, and then we showed how, which very nicely reproduces the power spectrum of the cycle for all the periods beyond 10 years.
mhm,
And of course, there is a 3 sigma detection at the period of 88 years, but you've got thousands of frequencies. So you expect one of them to have more power than you would expect from a 3 sigma, the way it's defined
mhm.
and considered by the people who claim this is a real detection.
Yeah. Okay, I see HMI has their hand raised.
Well, also, Robert, your hand's up as well. Do you have another question?
Yes, I have a question about the QBO,
Yes.
which is, I think, more interesting. And
Yeah.
then it's not clear to me if it's just noise or not. So I remember there's a paper by GA where she puts in purely random time sequence and she gets a plot which looks somewhat like this.
Yeah.
So how confident are we that the QBO isn't just noise?
Well, I'm not really certain on that. I know that there's been quite a bit of work. I know Kieran had a paper out that came last year, a year or two ago, showing showing this QBO for solar cycle 24 and how it's different in solar cycle 25. I'm not sure how you would necessarily be able to say, distinguish between noise versus some kind of physical effect. And then same thing for, the longer term periodicity. How do you distinguish between something that's just a characteristic of the noise in the system versus something that has some kind of underlying physical mechanisms?
Isn't noise just another word for something we don't understand?
Well, yes, but I think we
I
also
think
know
we-
that there's stochastic, by the nature of convection, you're introducing stochastic processes into how the dynamo operates, right? And so, there is a mechanism there that we could attribute the noise in this signal to, but I don't know, if we could definitively say that, there isn't some other physical mechanism causing that.
So the noise, so for the long-term periodicity of the 100 years or so, what goes into this model is the scatter in the tilt angle.
Yeah.
And the scatter in the tilt angle, yes, you can have this as a deterministic process coming from the convection, but the number of degrees is essentially infinite. So essentially it's random.
Yeah.
Okay, question from Cyprus.
Oh yeah, this is Jun Wei. Very nice talk, Lisa. It's very educational, but I guess still need a little more education.
Sure.
As we know, and as you mentioned, the polar strength at the solar minimum is a good indicator for the solar maximum, sensible numbers of the next solar maximum. So
Yeah.
what is the physics between these two factors? We know that the solar minimum is only about 4 years or 5 years away from the solar maximum. Does it mean that the polar field at the solar minimum is transported towards the lower latitudes in about 3 or 4 years?
Yeah.
I'm not sure if the interior equator marine circulation speed is that fast to transport the field to the low latitude in just 3 years or 4 years.
Well, it takes more than 3 to 4 years to transport the internal field from the high latitudes to the lower latitudes. We know that it takes about 2 to 3 years, for the field at the surface to make its way up to the poles. But this is not, an instantaneous thing. This is an ongoing process. So I think it's reasonable to think that the interior meridional flow might be operating on that 11-year scale. Robert, you have a comment?
You only need a flow of 1 or 2 meters per second.
Yeah, it's not.
How slow do you think it is? In when?
Well, depending where you are talking about, the location where you are talking about. If it's
So you want to move from 55 degrees to, say, 15 degrees. I think you only need a flow of 2 meters per second.
Yeah.
At what depth?
And I would say,
Yeah.
estimate at the middle of the convection zone, about halfway between the surface
Lower
and
half of the convection zone.
When I said where, I meant depth, not the latitudes.
About halfway down.
Is that
Right.
independent of the number of cells in the interior?
Well, if it's halfway in the middle of a convection, maybe it's doable. But if it's at the bottom, I think it's difficult to have to
So it's you need to average over whichever depth range you happen to believe the field is stored.
Yeah.
And this could be anywhere from near the base of the convection zone to anywhere near the top, really.
Yeah, it could be anywhere.
But
Back to my question, actually, I'm trying to ask what is the physics between the polar field strength at a minimum and the sensible number at the maximum. So you think that is the marine circulation plays the role to linking these two factors?
Yeah, certainly the marine circulation, I think, is what brings things back down to lower latitudes. But I mean, it's a complex process and interaction between all of these different things. I mean, you have to have that differential rotation shearing it. I think that the strength of the sea field, the start of that field, also dictates, how quickly are you going to see that emergence? So if you have a stronger field, polar field, you're going to see those active regions emerging at higher latitudes because you're able to build up that internal field strength a lot sooner than if you have them at lower latitudes. But in terms of asking a question, which part of the process are you talking about? If you're talking about how does the flux get from the high latitudes to the low latitudes, absolutely, I'm gonna point to the marine
I'm not
circulation.
sure I understand the question, because the polar fields at minimum, they're actually threading the whole sun.
Right.
They're not just
Yeah.
confined to the poles. The
Yeah.
flux is threading the sun. So I don't see why there's a problem with time scale to transport the flux.
So Yiming, you really think that the polar fields go down to the bottom of the convection zone or someplace and then come out the other pole?
yes,
Yeah.
I think so.
that's 100% clear.
I think
The-
they
Yeah.
I mean,
This is why I went to do helioseismology of the polar coronal holes.
I'm
Now, I think that there may be some cancellation that occurs, at the equatorial belts when you get those toroidal belts kind of colliding with each other. I don't know that there's not some kind of, but I think that certainly
if B is
there
equal to
can be.
0, then anything which goes in one hemisphere of the sun has to come out the other hemisphere. So at solar minimum, all the flux is basically concentrated in the polar region.
Yeah.
This flux is like a piece of string. They don't have ends. There's no end to this piece of string. It has to go in somewhere, come out somewhere else.
Yeah,
It
but
comes
at
out
solar
in-
cycle maximum, it's coming out at the mid latitudes, right, where the active regions are. You have most of it coming out there, and so
Sure.
as those belts
No,
get close
the
together,
net
right?
flux in the active regions is still 0.
It's not the net flux, it's the axial dipole, right?
So the net flux, so the polar fields at solar minimum have flux going through them, and this flux goes into the sun. It has to come out somewhere.
Right.
Near minimum, it has to come out the other end.
Right.
So yes, at least at minimum, field goes in from one pole, all the way through the sun, comes up the other
it's
pole.
exactly as Babcock drew it in the cartoon.
Yeah, and we don't know whether it goes through at the bottom of the
It could
convection
be,
zone.
I mean, it could be a very complicated pathway. That's
Yeah.
true, but
Yeah.
again, flux is conserved.
Yeah.
There's no end. There are no endpoints.
Yeah, no monopoles.
The symmetric part of the polar fields in the two hemispheres would be threading the whole sun, but the asymmetric part
Right.
would have to
That's
go
what's coming
in
out.
from one
Mhm.
pole and come out from low latitudes or the equator.
Right.
Yes, but that
Yeah.
component is weak at minimum.
Mhm.
But yeah, and you can have a quadrupole mode for the dynamo operating off that component. But
Yeah.
in solar minima, as we observe them at the moment, the field goes from one
One
pole
hemisphere to the other.
to the other.
It makes its way there. I'm not so sure that we know that it goes to the bottom of the convection zone.
No, it does. We
Doesn't
don't
have
know it
to.
goes to the bottom, but it makes no difference.
Yeah. Doesn't
So
matter what depth it is.
Because what you know is what you know is the amount which is getting wound up, the amount of toroidal field which is produced. It doesn't
Mhm.
matter where in the convection zone you're storing that field.
Mhm.
Because this is because of the paper with Manfred in 2015.
Mhm. All right. Any other questions or comments in the chat? Can't see, so I'm relying on someone there to.
Robert asked another one. Did you get that answered already, Robert? About the frequency points?
And then this was a different question. Was a question to do with Amy Norden's question or comment.
What was Amy's question or comment? I can't see. Amy?
Well, I just mentioned that there's a lot of papers and studies that show that the confidence levels at the QBO periodicities and the Riger periodicities are, 90%, 95% confident above a red noise power spectra or a white noise power spectra.
Okay.
And Robert asked how many frequency points. Well, I mean, it's all over the map, like some
Right.
people smooth over 2
Right.
years or
So my question
Yeah.
is, when you say something is that, for example, when you look at the 88-year periodicity, it's 3 sigma based on the usual definition, but we're looking at there's 1,000 possible frequencies in the range covered by the data set. So between 400 years and 10 years, there's many, many, many data points. And therefore, or 10,000 years if you look at the cosmogenic data. Many, many frequencies are resolved. Therefore, having one frequency, which is 3 sigma, is actually what you expect. As soon as you have 1,000 frequencies, you expect one of them to be at the 3 sigma level. And so my question is, when you say it's inconsistent with being red or white noise at the 95% confidence level, how many points are you free to choose from? Maybe I'm not clear.
Well, I mean, people use different data sets. Like right now I'm using the HMI magnetograms for solar cycle 24. And that's obviously going to have a different spectral resolution than something where you're using a sunspot area that's over 200 years. I mean,
So what I'm saying is, as soon as you have 20 different possible frequencies, you expect one of them to be outside the 95% confidence range.
okay. I mean, you mean, and that's not true? Or, I mean, are you saying you expect one of them to be outside the 95% confidence range and that's an error? Is that what you're trying to say?
No,
I think he's just trying to distinguish between something that is just a fundamental aspect of the noise versus some kind of requiring some kind of physical mechanism
All right, well,
to
you have
cause
to
that
assume,
periodicity.
you have to assume some sort of shape to the noise and see if your signal is higher than that. I don't really, and you have different time series that you're looking at, whether it's 100 years with sunspot area or, daily with magnetograms, you have different resolutions. I don't really understand.
Well, I think the point is that if you look at a time series that has variability in it, you'll always find some periodicity.
Right.
And I think that's what Robert is trying to say. And 80 is as good as any other.
Yeah.
So there will be one.
Yeah.
So why not that one? But my question was, haven't we seen the Weisbord cycle in much longer time period records, like the
Usoskin's looked at it and the
Also
carbon
the
record.
isotopes, I think.
Yeah, isotopes.
Beryllium-10.
Mm-hmm.
So it really is a longer record than just the sunspot number since the 1700s. It's a much longer one. So I think there's something more to it than that.
Yeah.
I had a final question about long cycle periods while we're on the topic. There's a lot of processes in the sun, there's a few. The diffusion processes, like magnetic fields, is like 10 billion years. The Eddington Sweet time is like a few 100 billion years. Is there anything to prohibit, I guess, on the timescale of the sun, which is 5 billion years, is there anything to prohibit a permanent, say, dipolar component to the dynamo? Do we know that the entire field reverses, or could there be, like, I don't know, a milligauss permanent field?
Are you talking like
Or is that entirely out of the question?
Yeah, no, I think that you're not able to. Are you thinking like a primordial field that might exist with the sun, but then does the dynamo process over top of that prohibit there being a primordial field? And my understanding is that it doesn't prohibit it. It's just that it's superimposed on over top of it, and so it's hard to pull it out, especially since we really can't get that deep into the sun at this point. But if anybody else, has any
Or
other,
even a non-reversing component of a Babcock latent dynamo.
yeah.
Is it entirely prohibited to have a steady component?
Like you're talking about like a
The
seed
cycle.
dynamo
No.
or that
No,
sort of.
he's talking about like a field that underlies the field that's oscillating. So for instance, if you, for instance,
Like a
had
frozen in thing.
like a frozen in primordial field that existed from, the core and in the radiative zone, where you don't have this cycling, where this cycling stuff isn't happening. And I think that is a very interesting question, because I think you could have it, but I think it depends on the tachocline, right? If you have a tachocline that's not very interactive with what's happening below that, then I think you might have the ability to sustain it. Whereas if you have a tachocline that kind of dips in there and there is some kind of interaction between those different layers, you might expect that primordial field might have some low level evolution associated with it.
Okay. Sounds
But
good.
I'm certainly not the expert on that. So,
I was just figuring if we're going 100-year cycles, we might as well consider billion years.
Yeah. Well, and I guess one of the things though is that once you start getting into those time scales, you have to start bringing in all this work that Travis has been doing, talking about how these physical parameters are changing. As the magnetic braking occurs, you're slowing down your differential rotation, you're changing the fundamental way that dynamo operates, you're changing how the convection works, you're changing so many different aspects that you're fundamentally changing the nature of the dynamo, and so those types of time scales, how do you separate that out? Well, you guys did a great job of filling in the extra time. I'm glad I left plenty of time for questions. I don't know, do we have any others in the chat or in the group?
Well, it seems like
Robert?
Amy and Robert still have more to talk about, but that may, since we're past the top of the hour, that might need to happen offline.
Robert, your hand is still raised. Do you have something to say still?
No, there was a mistake.
Oh, okay. I guess more discussions can go behind the scene offline. So we have a wonderful discussion and of course wonderful seminar first, and then wonderful discussion today. Thank you, Lisa, and thank you for everyone. So okay, so let's see you all next month at our next seminar. Bye. Thank you.